Welcome to Analysis of Variance, sometimes referred to as ANOVA in shorthand. And basically, we're taking similar logic for what we want to do with our familiar t-test, but the problem is t-tests are limited in some ways, and maybe we have data that asks a similar question, but with more means to compare, basically. And so then we're going to introduce analysis of variance with the idea that it really is where t-test is just kind of a limited solution to a fairly limited set of problems. Analysis of variance is a whole framework that we're just scraping the surface of the complexity of analysis of variance, and there's so much more you can do that we can't cover for this class. So my goals for today are to understand what analysis of variance is, how we can use it, and maybe understand through some of the mechanics how we could even go further if we wanted to. So here's what we're going to cover. We have to introduce what ANOVA is. Some things look different. It's got a different kind of table. It's got a different kind of distribution that we're going to be looking at. And we also have what's called a post hoc test, which we haven't really covered yet. But the same other things apply in terms of our basic hypothesis testing schedule leading up to a significance test, and then also not forgetting the sample size, or excuse me, the effect size and assumptions of the test. So first of all, let's just get introduced to the concept of ANOVA, what its goals are, how it's similar to what we've already covered, how it's building on what t-test can do, but unlocks a lot more potential than a t-test. First of all, what is a limitation to the t-statistic? Well, whether it's one mean, our independent, or our one sample t-statistic, or two independent samples means, or two dependent means, we're limited to just two means. Now, analysis of variance solves this problem because now you can test as many means as you want. So for example, you can have not just Democrats and Republicans, but you could also have Green Party and other different parties and means for each of those. Or for example, normally we think of gender as male versus female, but maybe you want to have 5 different kinds of gender on a survey that somebody could check. And that means you've got means for potentially 5 different groups. Analysis of variance really makes this not that big of a deal. Basically, we won't look at the raw data and calculating the statistics of ANOVA. For more complicated cases, you can just point, click, and shoot that in statistical software, which we'll see in labs for this class. But at least you can understand how the raw data that we use, the same rationale and mechanisms applies to many more comparisons of means than we're used to. So instead of a 2-level, what we call independent variable, mean 1 versus mean 2, for example, in the experimental design, we can compare a control group mean to an experimental group mean. In this case, we can just have a factor, and we're not just limited to a control versus experimental group. We can have a baseline of no treatment. The control is the placebo, the fake drug, and an experimental group, we can break that down into not just the real drug, it could be high, medium, and low levels of the drug. So in that case, with that factor of the drug and level of the drug, we can have as many levels theoretically as we want to have. A lot of times there's practical limitations to having tons of different levels, so we want to make it practically meaningful for getting enough means to make the comparisons we want, but not so many means that it becomes unwieldy and too much work. So basically, ANOVA can also be used for multiple factors. So for example, you could have your one factor of an IV that you manipulate of drug or no drug, placebo drug compared to real drug. But let's say you also want to have a therapy, like a talk therapy or person-to-person therapy. And that could also be another manipulation that you do within the same study. So therapy, yes or no, or it could control therapy of the previous compared to a new kind of therapy once a month versus twice a month versus 4 times a month. So you can really take your factor of therapy or drug and build in as many levels as you want. But as you can imagine, the more things you add, especially the more factors, the more difficult the math gets. And so we're not going to cover the actual math, but we will talk about how it could be used with multiple factors. Let's look at some ways analysis of variance might be useful for exploring. So first of all, exercise on life satisfaction. Here we're thinking of typically an experimental design. So a factor has 3 levels and we're manipulating whether you get no exercise, whether you're doing medium exercise, and we're defining that, and then high exercise, defining that. That's our IV, looking to see if manipulating that causes a change on life satisfaction. So in this case, we have a IV factor of exercise with 3 levels. And notice our life satisfaction dependent variable is more of a continuous. So our IV is a discrete variable, control, medium, or high exercise. So we can even call that an ordinal variable, whereas life satisfaction would be, you know, on a scale of 1 to 7 or 1 to 10, whatever, however we design a survey, we're considering that a continuous variable. Same thing for the idea of caffeine. We're manipulating caffeine into a ordinal variable, control, 1 cup, 2 cups, 3 cups. So again, that's a ordinal discrete variable. You can't just do 1.5 cups. You have to do what you're told to do for your condition. And then irritability would be more of a continuous variable. So interval level at the very least. Probably not a true ratio because irritability probably is never completely 0 for the human condition, but as long as it's interval level, it's a continuous variable for our purposes. And hopefully you can see here that we're using ANOVA for more than 2 groups, specifically a predictor or independent variable factor. So once again, trying to show how ANOVA is building on T. T compares the means in the numerator, and you're limited to 2 of them, 2 sample means, as we can see from our previous formula. Analysis compares variance both between and within groups. This results in a ratio, and that ratio is going to be F. So the idea is, especially what we're going to be covering in this narrated slideshow, is more similar to the independent samples. So independent samples T has 2 independent groups. Independent samples ANOVA can use 2, so we can do a T, that same data, and just point, click, and shoot in our statistics software and do a ANOVA. It'll give us the same significance result. It'll just do it instead of a T distribution and statistic, it'll give us an F distribution and statistic. But basically, we're looking at how much difference there is between sample means. Is there a big difference between mean 1 and mean 2, or mean 1, 2, 3, 4, different groups? And how much variance within, how much error is there that's within? So sometimes ANOVA is referred to as variance partitioning. So you have your total set of scores, and there's all sorts of differences. How many of it is attributable to what's differences between the groups, and how much is within a certain group, males or females, for example, how much of the differences in their scores just, they're different and we can't explain why. Well, that goes into our denominator, the bottom of our F equation. It's variance that's there, but we just can't explain it according to our categories or groups that we're using. You can also think of the ANOVA ratio as this. Once again, variance between sample means. We have multiple sample means. How different are they? That's the effect that we're trying to see is significant, if those differences are significantly different. And how much variance is there total, or not due to any treatment? So in this case, again, we're partitioning or separating our total variability. And you can think, if we just have a giant pile of scores, and then we can calculate a mean and calculate standard deviation, sum of squares, all that. But if we can take some of that total variability and take out some that is due to the between treatments, some of that variability is accounted for by knowing what group somebody is, whether they're, again, male or female, Democrat or Republican, in college versus not in college, all sorts of different groups you could put someone into. And of course, that's only going to explain some of the total variability. There's lots of differences between, again, boys and girls, or within Democrats and within Republicans. They're not all the same on tons of variables, and that's just variability that's there. That is just due to chance or not due to the group label we've put on them. So here's an example from a previous book I've used. This is the effect of temperature on learning. So temperature is, we're setting the temperature of the room or manipulating it into these three temperatures. And then we look at learning as sort of the outcome or dependent variable. And we can see learning mean for 50 degrees, pretty low. Learning mean for 70 degrees, higher. Learning mean for 90 degrees, low again. So we see that there's a difference here in the means. This is our between treatment difference. So we see the effect that we're already looking to see is, we know it's there. 4 is bigger than 1, 4 is bigger than 1, but is it significantly different? Well, that's why we have to think about the ratio. How much variability is within group? So we see these are not all the same values, as these within the 70 degree group are not all the same values. Why is this a 6? This is a 3 in learning. Why did this student learn at a metric that's double what this student learned? We don't know. It is variability in the scores that is within the group that we can't account for. And the more of this we have, it is the more noise that lowers our clear, significantly different conclusion that we'd like to make of the means between the groups. So once again, this is the numerator of our equation, basically our effect. This is noise, the difference of scores within groups. The more noise there is, the less we're clear that this mean difference is significantly different. We know it's different, but can we conclude that it's significantly different? So with ANOVA, again, we can do it with just 2 means, but we're assuming that we're comparing 3 or more means. So our hypotheses change slightly. Basically, the idea is null hypothesis says there is no effect. The population means of our 3 groups are the same. So for example, how intelligent, well, intelligence is a little bit loaded. Let's look at how many calories you eat per day. Is there a difference between whether you're an Ohio State fan or a Michigan fan or a Notre Dame or a Penn State fan? The null hypothesis is that no, there's not a significant difference in how many calories you eat per day based on which college football team you prefer to cheer for. The alternative hypothesis, though, is that at least one mean is different. Now notice we're not saying yet which mean we think is significantly different from the other mean. The F-test and the significance test only tells us that one of the means is significantly different from one of the other means. At least one. It could be more than one. Significance test doesn't tell us which ones or one, again, it could be either, is significantly different. So that's why we have to build in some extra steps for analysis of variance. So once again, we haven't specified which means are different, so we'll need a post hoc or after the significance test analysis, which sounds like extra work, but it's not that big of a deal. So with ANOVA, we're going to have a lot of notations and formulas. I'm going to go into more detail than I expect you to know for the exam, because it is a lot of stuff to, again, put together to solve one problem from raw data all the way to doing the significance test. What I want you to be comfortable with, though, is knowing the notations, knowing what they generally stand for, and then being able to see what does this piece of notation mean by itself, and what does it tell me when I see it in the formula that it belongs in. So hopefully, if you can get there, you're doing well for this class. So you can see a table quick of a lot of different notation. So again, we have to break down this data with 2 or more means in a different way than just the simple t-test comparing 2 means. So now we're in more than 1 mean or more than 2 means that we're comparing. We just had to break it down differently. So let's get started. K is the number of treatment conditions. So basically, we have a factor. How many levels of that factor are there? That's K. So clearly we can see K here is 1, 2, 3 treatment conditions. Little n is the number of scores for condition. So each of these conditions will have an n size. Now, most of the time it won't be exactly even with independent measures research, but for here we have even n sizes of 5, 5, and 5 for each of the 3 conditions. Not surprisingly, we need to have a measure of all the people together, and that is our big N, the total number of scores. So 5 plus 5 plus 5 people in each condition. And again, this is an independent design. So that means the scores in each condition are from different people than the scores in each other condition. There are 3 different classes. No student is in the same class. They're in one class and one class only. They're not in 2 classes. So that means we add them all together and we have 15 total students that we have scores for. We have also what's known as this T. This T is just kind of adding up all the raw X scores. So it's kind of like sigma X for each condition. Just add up the X scores, that gives us T. Then we have big G, sort of the grand total. So it's not a mean or anything, it's a total. And if we take the T, or the sigma X for group 1, plus sigma X for group 2, plus sigma X for group 3, T1 plus T2 plus T3 gives us our big G, our grand total of 30. So nothing super complicated here, just some new letters that we're introducing. Now we also have what's important to know is sigma X squared. So this is sort of a measure of, again, squares. We're going to need this in terms of calculating measures of variability, sort of like our sums of squares or having to square scores when we're doing our means and standard deviations, especially standard deviations from before. So we can't get out of squared territory, but it's often complicated to do all these, so often we'll just be given whatever the sigma of the squared X scores or squared raw values is. So the idea here is we need to find our sums of squares, which is a measure of variability, and of course we're partitioning that total variability into that we can account for between conditions that our mean differences explain, and then variability that our mean differences don't explain. So we have formulas for this. Now these don't necessarily make a ton of conceptual sense. So that's why I don't really spend as much time having students memorize the formulas, as long as you can explain, well, what does the G squared mean? Well, we have our grand total, and we need to square that to get our sums of squares total. Now, of course, that's our total sums of squares or total variability. We need to divide that into sum of squares within and sum of squares between. And again, conceptually, I don't have a great explanation for why these formulas get at what we want. As long as you conceptually understand what is sum of squares within, it's representing variability within this condition that we can't explain. I don't know why this person's a 3 and this person's a 0. They just are. I can't explain it. It has nothing to do with the temperature. What does have to do with the temperature is these different T values. So this T looks smaller. Learning is smaller for this group than this group. And learning is the same amount for the 50-degree group as learning raw scores are the total for our 90-degree group. So that I understand. That's variability too. This mean is different than the other two. Is it significantly different? Well, part of it has to do with how much difference within the groups there are. So again, we're setting up the ratio of within that which we can explain versus between variance that we can explain. Now we also have some degrees of freedom. This is where it gets a little bit more complicated too, but we have to know them to be able to use our, what we're going to introduce as our F table. So first of all, we have our degrees of freedom total, and this is our big N minus 1, our combined sample, total number of people minus 1. And then we have our degrees of freedom within. So essentially this is degrees of freedom within each condition added together. So since these are all 5, 5, and 5, 5 minus 1, 4, 5 minus 1, 4, 5 minus 1, 4, our degrees of freedom within is going to be 4 plus 4 plus 4, 12. So nothing too complicated there. Now we have our degrees of freedom between. So what is between? Well, our between is looking at variability between conditions. Variability that is explained by the mean differences, the average difference between the groups. And so if we have 3 groups, that's our K minus 1 degree of freedom of between is K minus 1, 3 minus 1 degrees of freedom equals 2. So hopefully you're following me so far, because it's very important to be able to at least identify the degrees of freedom for our analysis of variance moving forward. Now we compute what is known as mean squares. And again, this may not make a ton of sense compared to what we've done before based on the name, but I think you'll be able to, if you're following the difference between variability within and variability between, you'll be able to see what it means conceptually. So we have our mean square within, and we take basically our measure of variability within that we can explain, divided by our degrees of freedom within, to give us our MS within. And this is leading us, now we're leading to our actual F ratio or our significance test. Then we also have a mean squares between. So again, the interpretation is sum of squares between the variability that our manipulation or our conditions account for, and our degrees of freedom between. So now it's just an index of our between variability measure or metric. So now we can compute our F ratio. So we have to get our mean squares both for the within and the between components. Also, with any analysis of variance, we have what's known as the source table. And so this is where we put all the different parts together. So we have our sums of squares, both for between, within, total, and our degrees of freedom for between, within, and total. And then essentially our sum of squares divided by our degrees of freedom between. We have the formula for that we just saw, 30 divided by 2, 15. Within components, we have our within sum of squares divided by our within degrees of freedom, mean square of 1.33. And notice this is kind of like solving a Sudoku or some other kind of logic puzzle. If you don't have one of these pieces, you can use logic to figure out what the other has to be. So if we don't have our within treatment sum of squares, well, we know that 30 plus x, the between and within, have to equal our total. So if we didn't know this was 16, we can figure out that with these other two values, it has to be 16. Same thing with our degrees of freedom, or working from our sum of squares formula, mean squares formula, which is sum of squares divided by degrees of freedom, has to be the mean square. We can work backwards if one of these values is missing. So once again, we calculate these mean squares to get to our F ratio. So we put our mean squares between, this is the effect that we're trying to test, and our mean squares within, the variability that we can account for, that's more like our error term. If we are linking this to our t-test logic, and of course if our numerator is big, a big difference between our means, that's likely to lead to a bigger F ratio. If our mean square within our denominator is really big, that's likely to lead to a smaller F ratio. So both those factors are important. What is going to lead to the biggest F ratio? Big mean square between, small mean square within. That looks kind of like what we have right here. So given these components, this is probably going to be what we'll find to be, once we get started looking at cutoff values, a big F ratio. Very likely to be significant because the mean square between is so much larger than the mean square within. So we can already tell that our F is a lot more of a mean square compared to the mean square between compared to the mean square within, but is it significant? So that's why we have to look at the distribution of F ratios, and this is going to look different than our T distributions, but once we get past the initial strangeness, I think there's good rational reasons for why it looks the way it does and why we have to do it a little bit differently compared to our maybe cozy, familiar T process. So let's look at what F ratios are. Basically, our progression is looking at the variance between relative to the variance within. If the between is a lot bigger than the within, we're more sure that our between is likely significant. Their difference is significant, it's big, and we can see it. There's not as much noise. So that translates into our F ratio. And what does the different ratios potentially mean? Well, a ratio of greater than 1 means that our between variability is more than our within. Less than 1, or excuse me, I got this. No, I got this right. Less than 1 means that our between variability is less than our within, meaning there's not much to see, and there's a lot of noise or fog preventing us from seeing what little is there. And then of course, if it's 0, that means there's no variability to begin with, which is going to be almost impossible in most circumstances. What kind of a ratio do we need to allow us to reject the null? Well, it's kind of like our T statistic. How big does it have to be generally for our mean to fall in the critical ratio or critical region? So let's look at, this is our F distribution. How is it different from T? Well, clearly T had the peak right at 0. And there was, if it was the symmetrical distribution, T, and also going back to Z, peak was at 0, and then it would gradually have tails in the positive and the negative area. Now, F ratio, there can never be negative variability. 0 is the lowest amount of variability there can be, so that's why our F distribution can only have 0 or no variability to explain. Now, typically we see that ratio peak at around a little over 1, so equal between on top to within on the bottom gives us a ratio of 1, sometimes a little higher between. How much bigger does the between have to be relative to the within? Usually for our 5% or 0.05 alpha, this is a 5% chance that we're making a type 1 error if we reject the null hypothesis. Got to have F ratio of almost 4. For a more restrictive alpha of 0.01, or a 1% chance that we make a type 1 error, well, we need a much higher critical value, and again, a lot smaller part of the total distribution represents our critical region. It's very unlikely that a mean or an F ratio falls. I keep saying mean, we're dealing with an F ratio now, that the ratio falls at 7 or above, and that happens by sampling error. It's almost certain, less than a 1% chance that happened by error. in the other case, it's a 99% chance or greater that that mean fell here and we did not make a mistake if we reject the null hypothesis. So for example, we don't have one or two-tailed info because we're testing 3 or more means potentially, and how do we know where the bigger one is? It doesn't really make sense to think about 3 means or difference between 3 means in one graph. So again, that's why we have a ratio where we're just taking total variance and looking at how much between variance is there relative to the within. So for the previous example, we have an F ratio of 11.2, and we clearly see that it is very high F ratio, very unlikely to get that F ratio for temperature differences in classrooms affecting learning performance. Very unlikely to get that if the null hypothesis is true. So we feel very confident rejecting the null hypothesis, thinking that there is a real effect. The next question is, how do we get that critical value or cutoff value? Well, because we have 2 basically partitions of variance that we're comparing against each other, that's why we need to consider the degrees of freedom for both of them. So our numerator is, for example, our number of conditions, our number of conditions within our factor minus 1. So we had 3 groups, 3 temperatures for our previous example. 3 minus 1 gives us 2. So our degrees of freedom for the numerator is 2. This is the column that we're going to be choosing from, but which of these values do we need? Well, we need our degrees of freedom for the denominator, or our within component. And again, within, we had 5 people in each group, and 5 minus 1 plus 5 minus 1 plus 5 minus 1 gives us 12. So our within degrees of freedom is 12, and that signals us into our value. This is our 0.05. You can't see it on this table, but in the table in the back of your book, you'll see what alpha this corresponds to, 0.05. And I imagine this from the last picture is our alpha more restrictive. Then we need a higher cutoff value for an alpha of 0.01. So again, smaller cutoff value for alpha 0.05, but greater chance that we potentially make a type 1 error. A much higher cutoff value for alpha of 0.01, but if it exceeds this, we're pretty sure that we didn't make a type 1 error by rejecting the null hypothesis. So let's look at also hypothesis testing and effect size. We've pretty much figured out how to do the significance test. What comes next? So the basic steps are similar to what we've already been familiar with. For the hypothesis testing, state the hypotheses. Again, usually if we're dealing with more than 2 means, that just there's a difference somewhere in there as our alternative hypothesis. The null hypothesis would be that of all the means we're comparing, none of them are significantly different. We have to look at our critical region. How do we find that? Well, we need our degrees of freedom within and between, and then we can locate that critical region on our F table. Then we go through the steps to get the different pieces needed. Our source table, if we fill that in, we can get our F ratio, our mean squares between over our mean squares within, and then we make a decision. Now with the continuing to put in the actual values, we see our null hypothesis is there's no difference in this case with our factor. Our factor has 4 levels, 4 means that we're going to compare. So we can also see our between degrees of freedom is going to be our k, which is 4 minus 1. So our degrees of freedom between is going to be 3. That'll help us for our source table and also for our determining the critical region using our F table as well. And of course, the alternative is that there's 1 mean or more different. So then we have to locate the critical region. What is that critical value? Well, we have to know both degrees of freedom. We know our degrees of freedom here has to be 4 or k minus 1, but we don't know exactly what the within degrees of freedom is. We need more information for that. But if we think of what we're given here, 4 groups, okay, 3 observations per group. So 3 people in each group, little n minus 1 plus little n minus 1 plus little n minus 1 plus little n minus 1. So it would give us 2 plus 2 plus 2 plus 2. So then our degrees of freedom within would have to be 8 if we think about this logically. So now we have our different degrees of freedom, and we can find our critical value. So we'll see the actual number values on the next slide, and we'll come back to this. So we have, for example, our 4 groups. Our k is going to equal 4, 4 conditions. What is our big N? Well, 3 plus 3 plus 3 plus 3. We have 12 total people in here. What then is going to be our different values? Our t, for example, total for this group is 3. Total for this group is 3. Total for this group is 12. And total for this group is 18. Now, we can go through and calculate the sum of squares, but typically, even if we we'll have this given to us, so we don't have to calculate sum of squares for each of these different groups. What's our grand total? We add up all 4 of these t's to get our g, and again, hopefully our sigma x squared is just going to be given to us. So we'll see a little bit more of that in the slide to come. So we see, again, how do we get to our t's? We're adding up raw values or x's for each group. Then we're provided with our sums of squares for each group. We can see that our grand total is t for the 4 groups added up. And then we can plug these values in to get our sums of squares that we're going to need for our source table. So this is the first part of getting our source table. Now let's assume we've plugged in the values for those formulas, and now we have our sums of squares. We can do our degrees of freedom. Between is k minus 1, so 4 groups minus 1, degrees of freedom is going to be 3. And our within treatments, we figured that out. So n minus 1, little n minus 1, and that's 3 persons per each of the 4 groups, so 2 plus 2 plus 2 plus 2. Degrees of freedom between 3, degrees of freedom within 8. So then we can then plug that right in to get our mean squares. 54 divided by 3, and then 16 divided by 8. And then what's our decision going to be? Well, 54 divided by 3, if I'm doing the math in my head right, is that 18. So 18 divided by 16 divided by 8. So 18 divided by 2 is going to give us an f of 9. An f of 9 is going to be pretty big from the table and the f distribution that we looked at before. So we're probably going to conclude significantly different. Now let's also look at effect size. For ANOVA effect size, we have what's known as eta squared. That's what this n with the longer second bottom of the n. So again, variance accounted for. Why not Cohen's d? Well, because Cohen's d is based on just a mean difference of at most 2 means. And here we have multiple means we're comparing. So oftentimes, most of the time for ANOVA, more than 2 means. So our eta squared, we just go back to our sum of squares. And essentially, sum of squares between over our sum of squares between within. So again, this is our effect, the variability that is due to being in the different treatment groups. So this is the variability of the effect that we care about relative to the total variability. The variability that we care about versus the variability that we can't explain. It's people within a treatment, why don't they all have the exact same score? I don't know, but they don't. So there's some sum of squares within, and that's just some sort of error that we can't explain. So a way to look at that is a similar expression, is that basically our sum of squares between and within is our sum of squares total. So you can just swap out the different labels to get the same eta squared or calculated effect size. So if you want to go back to the last slide, you can then go calculate the R squared for the last example, because our source table clearly had the sum of squares between, within, and total. So clearly eta squared for analysis of variance is not a difficult calculation. Finally, once we've done our significance test and we've calculated our effect size eta squared, and again, eta squared is a variance accounted for, so bigger eta squared, meaning of all the variance, our treatment condition manipulation explains a lot of it or a little of it, but then we still don't know where the difference or differences between those means are, at least the significant ones, and that's where we need a post hoc test. So again, post hoc means after the fact, after we've done our significance test. Now you might be thinking, well, we have multiple means, why not just compare each of the possible mean comparisons with individual t-tests? The problem is that if you have three means, mean 1, mean 2, mean 3, you can compare t-test of mean 1 compared to mean 2, another t-test of mean 2 compared to mean 3, and a third t-test of mean 1 compared to mean 3. But the problem is if you run the same alpha for each of those tests, when you add up the total alpha for each of the tests, it becomes a cumulative 0.5 chance, or excuse me, a 5% chance that you've made type 1 error with any of the three t-tests you've done. But with the three t-tests, now your chance that there's a type 1 error in one of those three tests is already 15, which is usually way too high. So this is called experiment-wise alpha. Basically, the more means you're comparing, if you're just relying on the t-test logic means, the more comparisons you have, the more likely you're going to make a type 1 error. So that's why we have a post hoc test that adjusts for this automatically. Very simple and straightforward. We don't actually do the math for it, but we'll see it when we do a lab and see how that works. So our post hoc test, we have three options. So the t-test, generally there's some circumstances where you set ahead of time that I'm only comparing one mean to another mean, even though I have additional means in there. How often is that going to be the case, that you have multiple means but you only care about the difference between two of them? So plan comparisons is very rare. What you also have, though, is what's known as the Tukey and the Chaffee test. Basically, for our purposes, the Tukey is available and the easier option for more of our statistical analysis software. So the Tukey highly significant difference test is what we're going to basically be relying on. And the idea is that the Tukey test makes sure that of all the comparisons, of all the means you're doing, it makes sure that the overall alpha is exactly what you select. So if you select an alpha of 0.05, it means that of all those tests put together, there's only a 5% chance that you make a type 1 error. So it adjusts for more means to make sure it holds the alpha overall consistent. And so basically it'll tell you, is mean 1 significantly different from mean 2? Yes or no? Is mean 2 significantly different from mean 3? Yes or no? Is mean 1 significantly different from mean 3? Yes or no? And you can make all those conclusions and know with the Tukey test and the Chaffee test that there's only a 5% chance that in there's a type 1 error. So finally, as we start to wrap up, let's look at a final comparison of analysis of variance and t-test. What's kind of cool is the F ratio equals t squared. So once again, you can do a t-test and you can square it, and then in the same statistical analysis software, run your F test or ANOVA, and you're going to see your F ratio is the same as t squared. So what that's saying is that you can't cherry pick between, oh, a t-test is more likely to give me a significant result. A t-test has more power. By default, it won't. Now, there's some decisions you can make about a t-test. If you're, again, you can only use a t-test if you're comparing two means, that you could do a directional or a one-tailed test with t, and then maybe throws off this F equals t squared. But if you're assuming the default alpha of 0.05 for both and a two-tailed test for t, your F and t squared are going to be equal. So you can't just pick one and get a higher power. It doesn't really matter which one you choose. So once again, their process is a little bit different. Whether ANOVA, of course, using the F ratio versus the t-test, mean difference and standard error, but the results end up being the same, which is pretty cool. Basically, the assumptions of ANOVA are very similar, especially what we're covering here. Independent measures, observations within each sample or each group are independent. So if they're, if those kids in the different temperature classrooms are doing math problems, they're doing their own work. They're not all talking and working together as a team. That would break the independence of observations assumption. Also, that the populations are normally distributed for group 1, group 2, group 3, however many more there are. So you have to look, are some skewed and some normal? If they are, then you have to note that in your findings, saying that that might be a potential reason to trust our conclusions a little bit less. And also the idea of homogeneity of variance. So the idea that there's not a whole bunch of people there's a lot of variability in one group and no variability in the other. So for example, in the temperature group for the kids, it could be that kids in the 70-degree group have nice variability of learning outcomes, but in the 90-degree group, they're all hot and close to passing out, and so their performance is all basically zero. So if that is the case, you can't run your analysis of variance if one of your groups has normal variability and the other group has almost zero. And it's even worse than that. It means you've designed your study poorly and probably can't even use the data from that super hot classroom, no variability group. So anyway, a lot of information, a lot of ground we've covered for ANOVA, but hopefully you're comfortable seeing similarities between ANOVA and the t-test, and also the reasons for having to move into this new territory for the potential that it unlocks in a lot of more complicated research designs and analyses. So we'll be building on this for another version of ANOVA, the dependent measures. But other than that, we are a long way in our journey in one of the toolbox that is commonly used in statistics.